Ladies and gentlemen, good afternoon, good morning, good evening. I'm Jose Macharé. I'm chair of the Committee on Disaster Risk Management of the World Federation of Engineering Institutions, and I am very happy to welcome all of you and to manage this meeting, this seminar today. May we have the first slide, please? Today, our meeting will deal with the infrastructure systems for resilient societies. This is very important part of our work in the Committee on Disaster Risk Management. Today we have 5 outstanding speakers. 3 of them are members of the committee. Dr. Dave Branston, that is the vice chairman of the working group. He is from the New Zealand Lifeline Council in New Zealand. Also, we have Dr. Stefan Schauer from the Austrian Institute of Technology in Austria, and Dr. Carleen Bushdi from the Ghana Institution of Engineers. Also, we have 2 guests, 2 invited speakers, Dr. Yolanda Alberto from the University of Chile in Santiago, and Dr. Yoshihisa Maruyama from the Chiba University in Japan. They will share their knowledge and best practices in this subject. Next, please. In the program, we have a brief overview and then the case studies presented by our speakers, and we will finish with a roundtable and the key messages as recommendation for everyone. Okay, the last month, we present, the committee present a book dealing on engineering resilience in disaster risk management for sustainable development. It was launched in the 7th Forum of the United Nations, and a Spanish version with the support of the Colegio de Ingenieros del Perú. This book, next please, is composed by 5 chapters. The first on land use planning, the second on resilient infrastructure systems, the third on data and information management, the fourth on capacity building, and the fifth on institutional frameworks and public policy. We would like to share with all the public the main results of every one of these chapters, and invite other experiences to join us and to enrich the discussion. So with this, I would like to go directly to present our first speaker, that is Dr. Dave Branston from New Zealand. Please, Dave.
Thank you, Jose, and kia ora koutou. Greetings to you all. It's my pleasure to give you this brief overview of Chapter 2 on the resilience of infrastructure systems, to be followed by case study presentations by my fellow authors, and invited colleagues. This chapter focuses on physical infrastructure, water, energy, communications, and transportation networks. We regard these systems as the enablers of the other elements of societal infrastructure, such as health, finance, education, and governance. Physical infrastructure systems also have a high dependence on engineering and other technical inputs. The diagram on the right conveys the extensive interdependencies that exist between the physical infrastructure networks, and we're all aware of the potential for failures to cascade from one system to another. The nature and range of hazards that we're considering includes geophysical and meteorological events, climate change events, and system failures. The first, when we talk about geophysical and meteorological events, characterized by being sudden shock events that clearly are best mitigated before they occur, as opposed to climate change, which is an incremental phenomenon that requires adaptation over time. System failures, of course, are things that can happen as part of business as usual without external hazard events. The case studies to follow will illustrate this range of event drivers. Chapter 1 of the book sets out the key disaster risk management principles as they apply to engineering systems, including infrastructure. Just a brief summary of these principles in this slide. It's the focus on avoiding the creation of new risk, encouraging addressing that through better land use planning. Then there's actions to address the risk that already exists with all of our infrastructure in place. So this really focuses on the retrofitting of critical infrastructure to resist those hazard events. And then there's the actions to address residual risk, looking at the preparedness, things like the insurance and social safety nets. The greatest challenge with infrastructure really lies with our existing systems, which in many cases are aging and approaching the end of their life. This chapter advocates breaking down the challenge into essentially 3 key steps, focusing on understanding the vulnerability of the key elements of the systems, looking closely to evaluate the consequences of failure of the components. And that's firstly the operational consequences for the network. But more importantly, what are the consequences for the community? And then, having done that, identifying cost-effective ways of mitigating the vulnerabilities to prevent other risk of failure. And that involves predominantly pre-event mitigation, but also putting response plans in place after an event, should it occur. In order to illustrate the many facets of understanding infrastructure vulnerability and improving the resilience of networks, we now have 5 case studies to illustrate the different perspectives and learnings. Thank you.
Thank you. Thank you very much, Dave. We go into the case studies now, and for the first one, I will invite Dr. Stefan Schauer to present the power outage in Europe and South America in a comparison. Please, Stefan.
Thank you very much, Jose. Let me just share my screen. Does it work right?
Good.
Perfect. So thank you very much. Warm welcome also from my side to the audience. I would like to start off the list of scenarios and the use case descriptions with a comparison between power outages that happened in South America and let's say almost happened in Europe in the last couple of years. And as Dave already introduced, try to find some main takeaways from a technical and from an organizational perspective that we can learn from these incidents that happened in the past. So as a first scenario, I would like to talk a little bit about the blackout that happened in South America between the states of Argentina, Uruguay, and Paraguay in June 2019. You can see a very schematic overview on the main scenery. So what we have in this part of the region between Argentina and Uruguay is a network, power network that uses two hydroelectric power plants, the Salto Grande Dam and the Yacyretá Dam. Sorry, my bad Spanish pronunciation. So these are the main power sources in this area, and we have 3 500 kilovolt lines in this area that bring the power across the different states, so from Argentina to Uruguay. And in June 2019, we had the situation that there was one of the lines connecting Colonia Elia to Campania, which was under maintenance. And we had a second line that had a short circuit, which was going from Colonia Elia to Belgrano here in the south. So we had those two lines that were cut off, which led to the tripping of the third line that we have in this small part of the grid, which caused a major breakdown of the entire power distribution in that area. Now, the problem in that context was that the shutdown of the third line connecting Colonia Elia and Mercedes in the north, this happened due to an automatic generation shutdown system. So this was triggered by an automatic system, and the problem here was the system operated on false data. So the system did not know, was not aware about the maintenance that happened down here, and it shut down the 500 kilovolt line in the north, which caused the major blackout. Now, as a consequence, there was, of course, major impact on the water distribution, on health services and the transportation sector. For example, in Argentina, it was recommended to reduce the water usage for the amount of time. Some patients that were stationed at home, they needed to return to the hospitals because at home, due to the lack of power supply, their service could not be guaranteed anymore. And also local elections in Argentina that happened on that day were interrupted and had to be postponed for some hours into the afternoon. The whole thing was recovered after a couple of hours. So this happened in the morning of a day in June in 2019. Around noon, everything was, or most parts of the grid were again restored. So it was not a large amount of time, but still it had major impacts on different aspects of the social life in both countries, Argentina and Uruguay. As a second example, I took an almost blackout that we were experiencing in Europe in the early days of 2021. And the situation here was that 400 kilovolt busbar coupler that is located here at Ernestinovo in the region of Croatia, and which is connecting the power grid from Bosnia and Herzegovina, Serbia, and also Hungary in that region. This busbar coupler tripped, had an overcurrent, and due to the overcurrent protection was shut down. And as a cascading effect, the voltage, the electric power flows, they were rerouted to the neighboring lines. So for the neighboring lines, for example, here in Serbia, connecting Novi Sad with Subotica, there was too much power. Of course, there was an overload, so that caused this line to trip as well. Then there were several trippings also in Romania, as you can see, between smaller cities, and also tripping of the red lines, so which are 400 kilovolt lines in that area. And there were also some lines connecting Bosnia and Herzegovina with Croatia in this area that were tripping as well, as a consequence of the overload in the entire area. As a consequence, there was, as I mentioned at the beginning, a separation of the European power grid into a western part and an eastern part. And the problem then was that there was too much consumption in the western part and too much production in the eastern part. So what was usually a balance in the entire European network was now an imbalance in both of the parts. As a precaution, or as an immediate countermeasure, if you will, big consumers in France and Italy were disconnected from the grid to reduce the power consumption in the western part of the network. And in the eastern part, large generators in Turkey, they were also not shut down, but they had to reduce the production just to keep also the balance in the eastern part of the grid. By implementing these countermeasures, the situation could be quickly restored. The two separated networks could be reconnected again, and that's why it was an almost blackout. But still, if these measures did not work so fast, there could have been a major impact in Europe. Now, looking at these two very brief examples, we can draw some technical learnings and also some organizational learnings from that. So from a technical part, we see from the example in South America that automatic protective systems, although they are implemented in many, if not all, of the power grids that are operating now all over the world, it is important that those systems are configured well, that they have the correct information in place, because as we've seen, a misconfiguration in those systems can lead to problems and can create problems in the first place, as we have seen in South America. Shutting down this one line already cost the blackout. On the other hand, what was very helpful in this scenario, so in the South American scenario, was that the black start capability, so starting up without needing any external power supply, was an essential feature to recover very quickly from this blackout situation. So the hydroelectric power plants in that region helped very much. And if we look into Europe, which is a more diverse landscape, this could be more difficult to re-instantiate the entire grids and bring the grids back up to balance because of this diverse landscape of different power generating sources. From an organizational perspective, what we saw in Europe was that detailed emergency response plans, as the different operators of the power grids had in the different countries, they were very valuable in this crisis situation. So if you have to make decisions in a very, very short of time, these emergency response plans, of course, help very much. And also, as we've seen in this example, pre-contracted power shutdowns in different big consumers also support this quick reaction. So if you just have to initiate this shutdown without any big explanation, and also the organizations know what is at stake so that they shut down very fast, this also helps to restore the balance, restore the situation. And here, of course, also the cross-national, cross-cooperation is a core aspect in preventing these large power outages, which could be quite difficult in Europe with so many different nations on the continent. And here, what we encountered is that it's very valuable to have an interplay between the digital systems, so these automatic and preemptive systems, but also the personal contact, the personal communication, people just picking up the phone and calling somebody in France, in Italy, to shut down their power consumption, their organizations, is something that proves to be very successful to handle these situations. So this is just an overview on the first use cases that we had, and then back to you to hear more about the other use cases.
Thank you very much, Stefan. It's true, whatever the hazard is, always this kind of infrastructure are keen to suffer cascades events with other that involve other infrastructure systems too. This is for power networks. Let's see what in Japan they are doing on the gas and water supply systems. So please, I invite Dr. Yoshihisa Maruyama to present us the countermeasures of gas and water supply system against natural disasters in Japan. Please, Dr. Maruyama.
Thank you, Chairman. I am Yoshihisa Maruyama of Chiba University, Japan. Today, I'd like to talk on countermeasures of gas and water supply system against natural disasters in Japan. So today, I have two contents. One is countermeasures of gas pipeline system in Tokyo metropolitan area against earthquakes. So I will introduce earthquake disaster mitigation system called Supreme, developed by Tokyo Gas. This is an example of damage to gas pipes after the 1994 Northridge earthquake, United States. Because of this event, gas pipeline was damaged. Then the gas from a ruptured supply line burned, as shown in this picture. Then the water from a broken water main floods, as shown in this picture. So to avoid this kind of secondary accidents, gas supply should be suspended soon after when the damage to pipes is anticipated. Then 1 year later, the Kobe earthquake occurred in Japan. So because of this event, Osaka Gas tried to shut off gas supply soon after the Kobe earthquake. The Kobe earthquake occurred at 5:46 a.m. on January 17th. So Osaka Gas shut off gas supply in the blocks of Kobe 2 and 3 here at 11:30. So maybe approximately 6 hours later after the earthquake occurrence. Then lastly, they shut off gas supply in the block of Kobe 4 here at 9 p.m. So based on this record, it took longer than 15 hours to make decisions to shut off gas supply because of the lack of damage information during the 1995 Kobe earthquake. Yeah, before the Kobe earthquake, Tokyo Gas has Tokyo Gas has the earthquake disaster mitigation system called Signal since 1994, as shown in this slide. So as you can see, approximately 300 seismic motion observation stations are installed in their supply system. Then, based on the background of the Kobe earthquake, Tokyo Gas devised this disaster mitigation system to Supreme. In the Supreme newly developed disaster mitigation system, they have 4,000 seismic sensors in their supply area, as shown in this map. So using the huge number of records, they gather the earthquake information soon after the earthquake. And also Supreme estimates the number of damaged locations of low pressure pipeline based on the collected seismic motion and also using this kind of fragility function. So using this information, Tokyo Gas decide the locations of emergency shut-off of gas supply system. Also, they plan the restoration strategies using the disaster mitigation system called Supreme. So in 2011, we had a very, very big earthquake in Tohoku area, north part of Japan. So during this event, Supreme was activated as shown in this slide. So they could collect earthquake information within 5 minutes. Then Supreme could get enough information to perform its initial response. Also, Supreme estimated damage to gas pipelines and also evaluated the risk of liquefaction. This is a result of estimated risk of liquefaction. Yeah, according to the Supreme, in Chiba Prefecture, they have high risk of liquefaction occurrences, as shown in this map, around these areas. And these are the field photos taken by us, and because of this event, we could find evidence of liquefaction. So the estimated results are similar to the actual state, and the effectiveness of liquefaction estimation is confirmed because of this event. So second, I will introduce the countermeasures of water supply system against multi-hazards. For this topic, I will introduce ductile cast iron pipe with earthquake-resistant joint called HRDIP, hazard resilient ductile iron pipe. These are typical examples of damage to water pipes during the recent earthquakes in Japan. These two photos are taken after the 2011 Tohoku Japan earthquake, As you can see, the pipe joint was damaged and the water comes out from the water pipe. And this is the case of the 2016 Kumamoto, Japan earthquake. During this event, a very large steel pipe was damaged and the water comes from the damaged part. So based on the lessons of recent earthquakes in Japan, all types of water pipes were sometimes damaged during recent earthquakes in Japan. On the other hand, newly developed water pipes with earthquake-resistant joints were completely safe against large earthquakes. Yeah, this is a video of the ductile cast iron pipe produced by Kubota Corporation Japan. As you can see, the joint of this water pipe is very flexible and they are fine under the extreme large deformation as shown in this video. As you can see, the joint is very flexible and even though the large deformation is applied, there is no damage for the water pipe joint. This is the mechanism of the earthquake-resistant joint. As you can see, here we have protruded part. If the pipes are pulled like this photo, it blocks the deformation. Then the pipes are not stripped out. Even though if they pushed, the deformation is stopped here. So based on this mechanism, the pipes are not stripped out, even though the large deformation is applied. So they are quite flexible. So I will show one example after the big flood occurred in the western part of Japan. In 2018, we had big floods. Then, as you can see here, we have a very small bridge. But because of the flood, the bridge was completely collapsed because of the flood. But you can see water pipe is attached here. The water pipes were quite fine. Even though large deformation occurred as shown in this photo, but the water pipes are quite fine because they have earthquake resistant joint. So even if the large deformation is applied, they could not be damaged. So the ductile cast iron pipe with earthquake resistant joint recently used in United States in Los Angeles, as shown in this slide. For example, here, Foothill Trunk Line project, they use Los Angeles people use ductile cast iron pipe with earthquake resistant joint. Yeah, here they had earthquake fault, and the water trunk line is designed here to across the seismic fault. So if next earthquake occurs, maybe large deformation is applied to this water pipe. So they use ductile cast iron pipe with earthquake resistant joints produced in Japan. So this is the pictures during construction. They use water pipe with earthquake resistant joint. So this is the conclusion of my talk. countermeasures of gas and water supply system against natural hazards in Japan is introduced. First, real-time earthquake disaster mitigation system called Supreme was activated during the 2011 Tohoku Japan earthquake. And the initial responses of Tokyo Gas were properly performed due to Supreme. And the ductile cast iron pipe with earthquake resistant joints are quite fine under the extremely large ground deformations. Hence, they are safe against not only earthquakes, but also floods. So that's all. Thank you very much.
Excellent, Dr. Maruyama. Thank you very much. We will have some questions for discussions later. Thank you. We go through the next speaker. Please, we would like to know how things are going in Chile. So I invite Dr. Alberto Yolanda to present us about the risk and resilience on the water networks in Chile. Please, Yolanda, welcome.
Thank you very much, Dr. for the presentation and for the invitation to talk about what we are doing in Chile regarding risk and resilience of water networks. So first of all, I would like to start with one of the largest seismic events that happened in Chile. This work actually started as a data collection of several water systems in different countries. First Chile after the 2010 Maule earthquake, then New Zealand after the 2011 Christchurch earthquake, Japan in the 2011 Tohoku earthquake, and then the 2017 earthquake in Mexico. So the idea here was to collect information regarding the damage that the water systems experienced, focusing mostly on underground infrastructure and what soil deformation could cause in these areas. But later, the focus also was what happened during the emergency process, how the water systems were recovered, and how we are dealing with these results regarding what we can do about the water systems. So first, I would like to talk about the effects of the Maule earthquake in Chile. Here I am presenting the restoration curves for Concepción and Talcahuano in Chile. Both of them are cities in the area that was mostly affected by the earthquake and the tsunami. And here what we can know about these systems is that we have two private water companies that operate these systems. We have 4 million of users. It's about 7,000 kilometers of pipelines. And just in Concepción, which was the major city affected, there are 1,200 kilometers of pipelines. Most of the materials are mainly steel, cast iron, but also there's a large percentage of asbestos cement. And the idea before this earthquake was to start replacing most of these pipelines with HDPE in order to have a better response during the earthquake. However, during this earthquake, there was a lot of evidence of liquefaction, and there was also damage in other elements of the water system, such as tanks, pumps, and any other component in the underground infrastructure. So what we can see here is the days after the earthquake and the percentage of customers that remain without service. So you can see that in the city of Talcahuano, most of the people lost the service and they started regaining it very slowly. For Concepción, it was down to almost 20%, but then it started going to normal conditions after several days. In overall, it took almost 100 days to achieve a final reconnection of the whole network. So in here, what we were trying to do was to assess what happens with the system resilience, focusing on 4 aspects. The technical one that relates to what we are discussing about pipelines, soil deformation, and how it can affect this infrastructure. But we also have to focus on the organizational aspect. We have to think about these private water companies that operate the system and how they have to interact with the government in order to reconnect the service. And of course, thinking about the interdependence with other critical infrastructure, such as the electric network or the transportation. Then we have the social aspect. We are thinking about how people is actually adapting to not having the water service, how they are reacting to this, how their consumption changes. And then we have the economical aspect, thinking about how the resources that are available will be destined to cover the water service, either by using tanker trucks or by replacing the network and reestablishing the service. So for this, we are considering 4 elements of resilience that we can assess. First, robustness, that has to deal with what happens or what is the percentage of service that we are left with after an earthquake. Then we have the rapidity, which is how long will it take to go back to the original conditions. And then we have 2 other elements that are somehow part of robustness and rapidity, and they are redundance, which is how many elements are doing the same function in one system. And then the resourcefulness, which is how the people that works in the system are gonna work with what they have, either by talking about time, people, and economical resources to deal with the reconnection. So in overall, we had a 70% of service loss and 110 days to regain operability. So after we were thinking about this, we decided to focus not only on what happens immediately after an earthquake, so not only the emergency response, but we also have to think about what is the actual state of the network and how we can prepare not only the technical part for the water system, but also the governance. So in that sense, we were thinking about what is the information that is available, what is the actual state of the network, and some aspect that is very important is what is the current water loss that we have in the network. So in all around the world, we are usually losing some amount of water that is produced. We are thinking about going from 10 to 30% in most of the water systems. In Chile, in 2020, we got a report of almost 32% of water loss in the water system. So we have to think about how we could try to deal with this issue, so then the state of the network is better and well prepared whenever we have any disaster. So for this, we are trying to tackle this issue by going into 5 different modules. So this is a system that will try to get all the information necessary from the network and how we can actually reduce these losses. So first we have the operative module, in which we are gonna see how the network operates, what are the pressures, the demands that we currently have, what is the instrumentation that we could have, and then how we can manage that information. Then we have a hazard module in which we are analyzing what are the natural hazards that could affect the network, but also operativity hazards. And also we are talking about a very important factor, which is deterioration, and that actually impacts all the risk analysis that we could do in the water network. Of course, we have to base this on our hydraulic analysis. So we not only know what happens to the topological measures of the network, but also what happens to the functionality. And then we have a pressure optimization and leakage identification. And the idea for this is to be able to reduce all the losses, either from the current losses that we have whenever we have already leaks, but also from the preventive state. So for this, we can analyze what is the network damage, and based on artificial intelligence, we can also try to predict what it will be what is the behavior going to be like after several years and after several conditions. Then we develop scenarios of different hazards, and then we can assess either topological or functional performance metrics. And once we have this analysis for one network, we can make some informed decisions regarding where we can invest to improve this network. So focusing on the hazard model, which I think was the focus that we wanted to get for preparing in case of a disaster, we were trying to gather all the information regarding flooding, earthquakes, mudslides, and especially drought. We are having these issues in Chile. So the idea to recover water and to avoid these losses is to have a very robust database that can help us to identify the possible scenarios that we could have and the damage that we could experience in the network and how we could be ready to solve these issues. So for this, we conducted a study to gather geological data, hydrological data. We were conducting also scenarios of what could happen during several hazards, and also what happens in a multi-hazard scenario. So then we could assess what losses we could expect. And then the idea with this is that as long as we have information and we have an update of the network state, then we can move forward into this assessment and then to provide tools for the people who operate the network to be able to improve it. So for the risk analysis, we are considering these 4 elements. First, we have the probability of hazard. In this element, what we are thinking is that we can develop maps of these hazards. For instance, now we have seismic hazard, but also we have liquefaction maps. So we can assess what will be the damage for an underground infrastructure, either pipelines or tunnels, or if we are looking at other elements such as tanks, we can take a look at this hazard and then through the other elements, either by exposition or vulnerability, we can assess the damage. In the exposition, we are characterizing the infrastructure and the users. This is very important because sometimes in Chile, we might have very large cities such as Santiago or Concepcion, but we also have smaller cities that are that have a very small water network, but also we are thinking about redundancy and how this could be affected if we have any sort of outage due to this disaster. Then we have the vulnerability, and here we are working with a probabilistic approach. We are trying to develop fragility curves that will allow us to identify the damage that we have under certain scenarios of natural hazards. And then we will relate that intensity measure to the probability of damage of several elements. This allows us to gather different scenarios in the probability of having different performances in the network. And with this, we can also assess the probability of having certain consequences. So in these consequences, we are thinking about, of course, the economic impact, but also we think about the people affected, the losses that we could have, and how we are gonna deal with these changes in the performance. So we are not only thinking about the impossibility to provide a certain demand. We are also thinking about pressure, for instance, whenever we have an earthquake, we have to be prepared also for fires following earthquakes. So this pressure has to be dealt with, and we have to control these pressures even after these impacts. Then we can also think about the consequences regarding what are the resources that we have available, either by people who will work on the repairs, but also by thinking on what will happen with the different infrastructures that are connected with the water system. So for instance, during the 2010 earthquake, we had a lot of interactions with the transportation network and also the telecommunications network. There were issues after this earthquake that made it difficult to actually conduct the repair works for the water network. So this is something that we have to include in our research and that we have to work with if we want to create certain tools that can help the decision makers to provide a better service even after a natural hazard. So with these scenarios and with these elements of risk analysis, we conduct this analysis. Now we started first with toy networks, which was easier whenever we had to conduct probability analysis, and then whenever we had to also deal with artificial intelligence techniques. But now we are having information for real networks. And actually something that we realized during this work is that having this information and being able to update this information day by day and having the actual demands and the actual pressures that the system is working with is the most difficult part, because it's actually one of the things that has to deal not only with the technical aspect, but also with the governance. We are thinking that there is an institution in Chile that can regulate what happens with these private companies that operate the water systems. But in any case, like, there are only certain conditions that this government agency can guarantee. So in the other senses, we have to depend on these private companies. So we have worked with some of them. They have been willing to share their information and to share some of this data that we could use for the analysis. So we have started this analysis also with real networks. And we are able now to conduct dynamic analysis, which means we can simulate what happens in any kind of a scenario in different hours. So we have tried either rush hours, we have tried midnight, we have tried also midday. So the idea is that we can check what happens to different performance metrics. We check water availability, but we also check pressure. We also check other metrics such as entropic degree, which allow us to see what happens not only to the connectivity of the network, but also to the functionality. And with this, we can provide information regarding what are the most critical areas of a network, where do we have to do some investments, what are the points that should be the first ones to be repaired after an earthquake, for instance, but also we are dealing with the water losses. And this is very critical because some of the, first, our idea was to start with the earthquake hazard, which is very large in Chile. But then we realized that when we are thinking about the water system in Chile, the most difficult hazards to work with are actually those that are related to climate change. So in this regard, we are working with a focus on the water losses and how we could try to prioritize that we keep all the resources that are generated. So in this sense, we are thinking of how this system can actually provide new measurements for adaptation. We know that at some point we are working with this climate change reduction metrics, but we have to also prepare for adaptation. So the idea with this system is to provide this information for the decision makers to be able to decide whether to invest in displacing some infrastructure or reinforcing it. So then we can also provide elements for planning and design, knowing that we are constantly improving the network and we are constantly extending these water networks to cover other communities. So then now we can take into consideration what are the most important aspects regarding these climate change disasters. And then, of course, we are going into preparation and anticipation of these disasters by trying to take care of this resource. So again, in this sense, we are having to work with structural adaptation, which is our main focus, but we also include these administrative adaptation measures that can help decision makers. So what are some of the challenges that we have faced and that we are thinking that we will continue facing? First of all, the available information. I think that's the most important part because not always we have all the information that we need. Then we are thinking about asset management. Having the information and being able to use it during our analysis is great. But if we really want the government and every decision maker to being able to know all the data that is available and to know how to deal with this new information, we have to create systems that allow people to really assess what we have and to being able to manage the information, to manage the current state of the network, and of course, to exchange information with the most important actors of this network. We are also thinking about emergency plans. Of course, this is difficult because we have to think about this public-private partnership that has to be generated between the private companies and the government. And of course, we are thinking about prevention and reconstruction, which will be at some point unavoidable. And then we will have to work with how we can create a more resilient system even after a hazard. So thank you for your time. And yeah, we'll be welcoming any question after the whole presentation.
Great. Thank you very much, Yolanda. We go directly to profit the additional time for the discussion. We come back with Dr. Dave Branston, please, to know about the infrastructure lessons that we have learned from recent major earthquake in New Zealand. Please, Dave.
Thank you, Jose. New Zealand is situated on the boundary of the Pacific Plate and the Australian Plate at the bottom of the Pacific Ocean. And this interface has been the source of many major fault rupture earthquakes over time that has shaped the geology and geography of New Zealand. And it's the reason for our high seismicity, which is the same level as any of the countries around the Pacific Ring of Fire. Having said that, we didn't experience any earthquakes affecting our major centres for more than half a century until last year. And the earthquakes I'm going to briefly tell you about affected the city of Christchurch, which has a population of 400,000 people, and a rural tourist area of Kaikoura. So this started in September 2010 with the first earthquake of the Canterbury Earthquake sequence. It was a magnitude 7.1 earthquake which occurred out here, well away from the city, but it shook up the whole of the region on a previously undiscovered fault. That earthquake didn't cause any loss of life, but in the course of the next 18 months, there were more than 50 aftershocks of greater than magnitude 5, quite an unprecedented sequence, including the devastating magnitude 6.4, which was a direct hit on Christchurch, caused the loss of 185 lives, most of them in the building on the left. And again, lives were lost in landslides along the lines shown on the right. The main feature of the sequence was the repeated and widespread liquefaction across a large area of the city and the surrounding districts. This led to the loss of many houses due to the effects of settlement and stretch, and significant damage to roads, as you can see in the middle there, and all the underground services within. However, the image on the right is of a electricity substation, which, despite significant settlement of the ground around it, managed to carry on functioning. But as you can imagine, there was an extensive recovery that followed this event. But just as that was advancing, another significant earthquake occurred 5 years later, north of Christchurch in the Kaikoura district, and significantly affected the landform. This earthquake saw up to 20 faults activating, with 14 faults rupturing, that gave rise to ground displacements of more than a metre. Just to give you a feel for the extent of the earthquake, the greatest displacements were near the coast, were actually 12 metres horizontally and 5 metres vertically. And I'll show you some impacts of that shortly. But our capital city, Wellington, was also significantly affected by the distant shaking, somewhat akin to the Mexican earthquake in 1985, where the city 200 kilometres away still took significant damage. But the nature of the faults in the epicentral area affecting largely houses and smaller buildings, but in Wellington, our major port was significantly disrupted due to liquefaction from the long duration earthquake shaking. And again, along the coast, our state highway network was significantly affected by a multitude of landslides. This is the railway track buried under that landslide, and the railway track buckled at one of the 14 faults that ruptured further along. So this took both earthquakes took an innovative approach to the infrastructure rebuild. And in the early stages of the recovery, in following the Christchurch earthquakes, there's recognition for the need for a contractual approach for community infrastructure that's less controlling, less risk-driven than customary contracts. And so this led to the development of incentivized industry alliances for the rebuild of public horizontal infrastructure, predominantly water and transportation networks. So this led to the formation of the Stronger Christchurch Infrastructure Rebuild Team, known as SCIRT, which was a collaboration, a partnership involving funders, central government and local government, the network owners, where they were outside of government, and contractors, a number of contractors capable of contributing, were all put together in quite a unique alliance. The success of that over the subsequent 5 years led to the creation of a very similar alliance to help rebuild the extensively damaged state highway and rail corridors following the 2016 Kaikoura earthquake. Back to the Canterbury earthquakes, just to give you a sense of scale, the alliance there replaced or repaired more than 630 kilometres of sewer pipe, 100 kilometres of water pipe, 114 pump stations were completely reconstructed with all the associated roading. So the key learnings, just to summarise a very long decade for infrastructure post-earthquake rebuild in New Zealand. Again, looking at this through lens of technical learnings and organizational learnings. One of the features from the Kaikoura earthquake was to not just rebuild buildings and bridges exactly where they were. It was taken as an opportunity to reduce future hazard by choosing wiser locations and rerouting or different locations. And whilst the familiar mantra for disaster recovery is build back better, sometimes build back differently is an equally powerful philosophical approach to avoid revisiting future risk. One of the many learnings from the Canterbury earthquakes, where the city had a red zone precluding people from accessing it for more than a year due to the hazard posed by partially damaged buildings. In the days following the earthquake, where power was out, the telecommunications networks, particularly the cell towers, were being run from standby generators. And there were real challenges for those telecommunication companies to get access to actually refill the storage tanks of those generators. And so after the event, they have significantly increased the size of their fuel storage tanks in metropolitan areas. Under organizational or contractual learnings, I've already spoken about the benefits of an incentivized alliance involving funders, central and local government, network owners and contractors. A lot of thought has been given now to the benefits of that, being prepared to initiate that alliance immediately after a future disaster, but also how this can help us with infrastructure mitigation before a disaster. Overall, the importance of relationships and collaboration and people working together in different and innovative ways. Thank you.
Thank you. Thank you very much, Dave. Very clear, and it was really exemplar what New Zealand have achieved after these events. For the last formal presentation, I want to invite Dr. Caroline Bushdi for the presentation on the role of the codes and standards that are important in the infrastructure design and the resilience. Please, Caroline.
Thank you, and greetings to all. So I'm looking at the role of codes and standards, and these okay. Sorry, I'm just trying to get my slides to move. Okay, good.
It's okay.
So we're looking at the role of codes and standards, and the codes and standards that we've been using for infrastructure are generally specific to different elements of infrastructure like buildings, bridges, and roads. And they've contributed quite a bit to the resilience of communities by ensuring that we have minimum levels of safety and health. And if you look at building codes, for example, or seismic design codes, they've been quite successful in reducing loss of life from building collapse in the areas that have enforced their use. And we have examples like Chile, the earthquakes in Chile and in Japan, where because of very strict enforcement of the codes, they were able to reduce the loss of life when they had earthquakes. But there are some challenges in the use of these codes and standards. the development of codes and standards, for example, involves very, very significant human and financial resources, because you need to have, they're based on extensive research. You need to have good technical knowledge. You need to have a very deep understanding of potential hazards, and all these are costly. And therefore, many countries are unable to afford this, and they just take codes from the better resourced countries and adopt them, and adapt them too. But there are countries that just adopt the codes as they are and may not even be able to adapt them to suit their own environments. But the recommended building codes, especially, most countries recognize that they are very important for life-saving purposes, and you can find them in almost every country. But that's not the same for other codes that cover the non-building elements. These are not always available in every country. Also, we find that in some countries, the codes are not backed by regulation. So you also don't have strict enforcement of the codes. And then it happens that you have buildings that are put up that do not comply with the codes that are recommended. And a particular problem is also created by infrastructure that's already in place before even the adoption of codes. And this is because retrofitting these structures can be very costly and difficult to enforce. So we have these difficulties with the codes and standards, and improving resilience will also require that we ensure the continued functionality of critical infrastructures, critical infrastructure systems. As has been said by other speakers already today, you find that you have your water systems that rely on electricity, and then the electricity systems may also be required for functioning of communication systems and so on. So these critical infrastructure systems are often interdependent. And to improve the resilience, we may need to establish performance requirements for these infrastructure systems. And we recommend that we use a framework approach to develop internationally consistent standards. The codes must also address the continued functionality in buildings, because often these buildings are the nerve center for these infrastructure systems, and we cannot just go with life safety alone. The buildings must continue to function properly. So in summary, we are saying that codes and standards have been quite successful in addressing issues like safety, and they've contributed to the resilience of infrastructure. But countries must be encouraged to adopt specific standards, not just for buildings, but also for non-buildings infrastructure, and also back them with the right regulation and ensure that the standards they adopt are appropriate for the environment. We also recommend that new standards are developed that define the performance requirements for critical infrastructure systems. And we recommend that this is done using a framework approach. The continued functionality of essential buildings also needs to be addressed in the codes. We need to go beyond the life safety provisions. Thank you. So these are the main key things we want to say about the role of codes and standards. Thank you.
Very good, Caroline. Thank you too. And now we will proceed with a roundtable. So every one of the speakers may exchange or ask to each other. Meanwhile, with Lisette, we will be looking for some specific questions from the public in the chat log. As Vice Chair, maybe Dave, you can animate some specific or something that should be reinforced among our other colleagues.
I think it's one of the features that the presentations have highlighted is the need for organizations to be connected up with other utility organizations and the community. I think resilience is not a state that an organization can achieve working in isolation. And I think all of the case study presentations have really highlighted that point. And it's really important equally for infrastructure providers to be working closely with the critical customers, thinking particularly of community facilities such as hospitals, to make sure that they have appropriate backup arrangements for those situations where utility outages occur for whatever reason. And I think this is an important point that needs to be re-emphasized. Rather than risk management can sometimes be treated narrowly within organizations, resilience requires a much broader collaboration.
Yes. I would like to ask Dr. Maruyama about more or less how much of the water network in Japan has been renewed with this fantastic system that you have shown us with these special joints. What is the percentage? Is just starting, or is the whole Japan now equipped?
In Japan, the water pipes are getting old, so we are renewing the older pipes. In average, percentage is less than 1% in average, and most of the newly installed pipes are good pipe against earthquake or earthquake disaster. I don't say that all pipes are the pipes with earthquake resistant joints, but we have two kinds of good pipes. One is the ductile cast iron pipe introduced today, which I introduced today, and the second one is a polyethylene pipe. They are also strong against the earthquake. So the newly installed pipes are mainly using these two pipes.
Okay. Very good, very good. There is a question from from Engineer Basilio. I take it this is surely for Yolanda that talk about the curves, the vulnerability curves. In fact, it was from okay, don't have the name, but they ask the question is which is the methodology that you're applying to estimate the factors of the damage factors? You have maybe read the question for these curves concerning to the type of hazard.
Yeah, for sure. So what we do is use a mix of an empirical approach and an analytical approach. So first, for the empirical approach, we collected all the damage data after different natural hazards to see what was the response of the elements. But then using the analytical approach, we develop a scenario and we have to develop thousands of scenarios to see what happens with the intensity measure that we consider for damage depending on the element. So for instance, when we think about the earthquake hazard, we are thinking of an intensity measure of ground motion. So probably for underground infrastructure, we think about the peak ground velocity. And then we develop maps of peak ground velocity based on these probabilistic scenarios. So then we can assess what happens with a model of a pipeline and what will be different damage states regarding the formation in this pipeline. So in that sense, we can obtain the probability of exceeding certain deformation, and then we get these fragility curves. And we can complement that with the empirical data. When we think about other hazards, for instance, when we think about tsunami or flooding, we are thinking about a height of an inundation height. So then we can think about how this height will impact the infrastructure. So either we can define state damages based on a binary state, like either it's working or won't be working after this, or we could also define state damages based on how this infrastructure could, or this element of the infrastructure could remain working. So for that, we also develop probabilistic scenarios, and we support those values with the empirical data that we have so far. So the idea is to work with this approach for all the elements until we have fragility and vulnerability curves for all the elements in the system for different hazards.
Yes, thank you. Yes, it's very clear. There is a more general question. Maybe some of you would like to give an opinion. It's quite general, but it's on how to build resilience against the climate change, knowing that climate change is not a specific hazard. What are your opinions on this? Or is a complete public policy specific for the whole climate change effects in every country? Who?
So if I can
Yes, go ahead.
quickly again, just thinking from the water system point of view, there are several hazards that come from climate change that will impact the water system, especially thinking about how we could meet the demands. In Chile, we are facing a drought, so this could severely impact what is the access of water to the people. So of course, there are several ways that we are thinking for the infrastructure and the technical aspects of how we could create some adaptation for climate change. But certainly, I think the idea to face this issue has to be in a whole. We have to think about governance. We have to think about how the organizations will be working together and what are the policies that they can work with. And we have to think about the resources and how people will adapt to these different ways of dealing with climate change. So I think there has to be really a certain set of policies, but also regulations. And also we will have to work with how organizations, maybe even the organizations we have so far are not enough to deal with this issue as it is. We will have to create new ones that can actually focus on this aspect and being able to do the asset management, but also deal with the technical aspects and at the same time meet the conditions for climate change. So it's a complex problem that I think we'll need several actors to solve, even not to solve it, but just to reduce the impact.
Yes, yes, I do agree too. Stefan, and how the type of contracts between the providers of infrastructure, for example, in electricity, power, within the from country to country or company to company across the country boundaries. For example, in Europe, and is it applicable to other places?
So I think it is quite important to have a look at how the critical infrastructures operate and cooperate within a state and also across states. So it might be much easier within a nation, so within a state, because the actors might know each other. You would have national regulations, but when it comes to supranational organizations like the European Union, I think we need a lot of guidelines and maybe also some directives or something in that context, just to give guidelines and also to help the organizations and pave the way for them to cooperate in a way that they can be prepared and that they can also share information and share data and knowledge about their networks in a common and in a secure way, so that they can interact more properly and prepare themselves against power outages, which I think will be happening more often in the future due to things like climate change, and also the measures that we are taking, moving more into the renewable energy sources, which might be more volatile, more fluctual when taking the entire grid into account.
Yes, yes, of course. Well, thank you. And maybe Yoshi, he's made comment in Japan, where I imagine most of the contractors are private, from the private sector. What is the role of the government, of which is the government body that controls or that norms the standards of for the contractors, both in installation and in operation, to assure the resilience of and the continuity of this infrastructure?
The comment is for me. Sorry.
Yes, it was about the control or the supervision that the government has on the private companies providing infrastructure, both in construction, in building, and in the operation.
Yep. As for the gas and water in Japan, gas supply is performed by private company mainly, and the water supply is done by local municipalities. Yeah, and as far as I know, the instructions or codes may be provided for water supply is provided by a sort of governmental institution. Yeah, and the current problem of Japan, the number of population is decreasing in some local municipalities. So it is difficult to run the water supply by one municipality. So therefore, sometimes some small municipalities get together to run the one water supply company. Yeah, it's different Japanese governmental issue for infrastructure.
Okay, I see. Thank you very much. We have a question or an opinion from Brian Sharman that said good asset management practice should be applied consistently globally using ISO standards, and the International Infrastructure Management Manual has encouraged the identification of critical assets and critical customers for some years now. It's in the sense of an answer for one of the questions. There is also a question that is quite maybe a quite local problem or at the national level, that there are some countries, and this is a problem that Carlene talked about, some countries are not able to develop their own standards and codes for every type of infrastructure. So they copy simply the other codes or other ways to build. So I think that this has been discussed that with and I go, excuse me, because I go through the next question too. It's part of the answer. That a close cooperation is needed in not only between country to country, but in this kind of global panels of professionals, because there is a question on if the professional groups, I imagine that he refers to is the question of engineer Samuel Body, that said, I would like to ask whether or not pragmatic steps are being taken by various professional bodies to ensure that current infrastructure development are resilient and respond to the dictates of SDG 11. Maybe Dr. Branston can add on this what professional bodies are acting on this.
I think indeed, as you say, Jose, the two questions are closely linked, and agreeing with Brian's comments that for companies that follow good asset management practice, a lot of this isn't new, but it's at the community level needing to have the infrastructure providers following as common a process as possible, including how they are responding to the Sustainable Development Goals. That really behoves infrastructure companies to work together rather than working in isolation, and hence the professional organizations within each country have quite a role to play in facilitating these discussions and ensuring that the Sustainable Development Goals are being taken on board by individual infrastructure providers.
Yes, that's right. From my part, last question to Yolanda, that is considering that the most of the modernization of the infrastructure that you have shown to change all the pipelines or most of them for the new type after earthquakes, after affectation, who pays this? Is the state, the government, because the companies are private companies that operate this? How are the deals on this, if you know?
Yeah, well, actually, this is a very complex issue because, and especially when we think about prevention and mitigation measures, this, like from the technical point of view, it's a complex problem, but once we find a solution, it comes to this: who's going to pay for the changes? Who's going to pay for the mitigation measures? And the thing is that in this sense, and I think Carlin could provide some information regarding these norms and codes that could be helpful for this. But the thing is, at this point, the idea is who has the responsibility. So in Chile, we have this government agency that can regulate what happens with the private companies that manage the water, but they cannot force them to actually make all these improvements or to change all the network, which first of all, like changing the whole network would take many decades because we have a very complex system as many other countries. So the idea of just changing the whole network, will consider a very significant time framework. But the thing is that when we have to decide who will pay for this, there should be some regulations, because otherwise, like people will try to deviate from this and try to assign these responsibilities to someone else. So the thing is, of course, at some point, there should be a contribution of everyone, the government, the private companies, because they are managing these assets and they have to keep them in a good condition. But also there has to be a contribution of the users. So some of these changes have to eventually go into the cost of having the service. So, but what is the part that has to, or that each sector has to contribute to? That's the difficult decision, and that's something that really needs regulations, because when we think about other matters, there are coverage for these, there are codes and regulations, but when we think about disasters and risk mitigation and resilience, there are still not clear regulations of how this can be done and who has the responsibility. And everyone wants to reduce the risk and everyone wants more resilient infrastructure, but nobody raises the hand when it comes to pay.
Okay,
So,
okay, thank you, Yolanda. Before going to the end and some conclusions, I would like to ask Carlene if you can clarify. You talk about the non-building infrastructure. What were you referring to?
Okay, non-building infrastructure like bridges, dams, towers, and all those other kinds of structures. So in most countries, everybody recognizes that buildings are important for life safety. So they will have the building codes that they recommend, but they may not necessarily have for all the other types of structures. So,
Okay, okay, I understand. Very, very clear. I would like now to ask Dr. Dave Branston to go through some key comments, some key or final kind of conclusions, and knowing that we will use all the discussions from today, that is one of the objectives of the meeting, to use the discussions that we have had to include them and to enlarge the previous key conclusions or key messages that we had for and are published in the booklet. Okay, please, Dave.
Thank you, Jose. And I'm just going to briefly highlight some key messages, both within the chapter of the book, but also that have been brought forward in today's discussions. If we can go to the next slide, please. One of the key overall messages is the importance of understanding the different components of what makes infrastructure resilient. Our minds invariably think of the physical attributes of a network and have the importance of having robust assets and networks with redundancy, as Dr. Alberto covered. But as she also showed in one of her diagrams, looking at the other things that make up a resilient network. And one of the key things we've learned over the years, particularly in New Zealand, is that second point of you need to have appropriate resource commitment by infrastructure organizations, firstly to understanding vulnerabilities, and secondly to developing appropriate mitigation measures. And the third point is the point I made earlier. Resilience isn't something which can be conducted within organizational boundaries. It requires effective collaboration with all related infrastructure elements and the stakeholders. And this applies both to, it obviously applies to prior to a big event occurring, but those relationships also carry through the response and recovery. But the other important element is again, the connection with those key community customers, both at the household level, but also at key institutions, making sure those facilities that you don't want to fail under any circumstance actually have appropriate preparedness in measures in place. Next slide, please. And so all of those resilient elements in the previous slide provides different opportunities to improve, to understand and improve network resilience. And some of them involve relatively modest cost. The interaction and collaboration doesn't have the same price tag as replacing sections of network, even though they're both part of the equation. And we just had the discussion around the understanding the different characteristics of an organization that is privately owned, perhaps operates under a regulatory environment, as opposed to the more community-owned infrastructure, such as water networks. And we need to tailor the approaches to addressing resilience challenges differently for those sorts of organizations. And as Dr. Skauer outlined in graphically with the cascade failure presentation, the importance of understanding all the dimensions of the interdependencies. And again, that speaks to organizations working together. The last point is all about when new infrastructure is being committed to, making sure that it's not just put on the same site that historically that infrastructure has been at. New infrastructure development provides a prime opportunity to reduce future risk. And this is a particularly important theme for in relation to climate change. So to summarize, the key overall theme from this section of our document, and indeed this session, is the importance of focusing on organizational relationships and for infrastructure providers to work together collectively on resilience. And for us as engineers, the main message is for us to be constantly aware of the opportunities to improve the resilience of infrastructure systems when they come around. Thank you.
Okay, thank you once more. And okay, we have done, we really appreciate a lot the contribution of all of you. If I before say goodbye, a special thanks to our 3 members of the committee for your great work within the book and the presentations today and the discussions, and also warm. We are grateful with Dr. Alberto and Dr. Maruyama for sharing with us your experiences. And this is a great contribution for this working group. Thank you to all of you. I will ask you to, Lisette, maybe put or to the technical, to have a final photograph of all the speakers, and before giving the announcement of our next. Okay, please open your cameras. All
miren a la pantalla, por favor. Ahí está, una sonrisa, excelente. Muchas gracias. Listo, doctor.
Gracias. Thank you. We, before say goodbye, would like to announce the next webinar. It will be from now in 1 week, and is presented, has been organized by the working group on institutional frameworks. Maybe we can project, please, the flyer. And is the institutional frameworks and public policies for resilient societies. And we will have the vice chair of this working group, Dr. Mais Lin, and 3 guest presenters for this. We will share with you this flyer. And thank you very much. Thank you for taking this time with us, and have a great day and week.